morning, everyone. Thank you for coming here. I want first to address the fact that I'm not the author of this study. I'm presenting the study on behalf of my colleague Francesco Carino, the author over here, which unfortunately could not be here today. But I'm quite aware of the topic, and I discussed a bit with him, so I should be able to answer all the questions you have. And if not, I'll give you his mail at the end of the presentation if you have any specific questions you want to address to him. So this is a common work between Francesco Carino, Alessandra Omar Bourlet, and Elena Muccialini from the Human Tech Institute in Fribourg, as my colleague mentioned before. The name of the project is LoRaLoc. The idea is to use machine learning to improve the geolocation of LoRa systems. A few words about the outline of the presentation, just to highlight it. I'll first start with the context and goal of the project. Why did we do this project? I'll then continue by defining a bit the methodology that we use to get the result that we obtained. And then I'll show and present a bit the results and try to explain or describe a bit the kind of results that we obtained. And then I'll finish with the conclusion and perspective of the work that has been done here. So let's start with the context and goals. So the context of the project is mostly Internet of Things, all the objects that are in place in the environment, small objects, and geolocation. There's quite a few opportunities because now there are more and more IoT objects around outside, and these objects often need geolocation, right? The current system that's being mostly used to geolocalize these objects is GPS. But as we know, GPS consumes quite a lot of power, and for small objects that are dispatched in the environment, this is not really ideal. And of course, it only works outdoor. As soon as you enter a building, GPS does not work anymore, and this might be a problem for some applications. Recently, there has been the transmitting protocol or data communication protocol, LoRa. I don't know if you're all aware of it. It's quite trendy right now. It's being deployed in many cities in Switzerland and in the world, and it's seen as one of the promising technology for IoT. LoRa is for it's the acronym for long range. It's a low power consumption. It's been developed to transmit small amounts of data, so not huge data transmission, but really with a low power consumption in mind. So it's really something very interesting for IoT objects. And something good with it, it could be used indoor. It will be potentially be usable to do geolocation indoor. One of the main problems with the current LoRa solution being now available is that geolocation is actually about 50 meters, 30 to 50 meters. GPS, just to remind you, is about 5 meters precision, 5 to 10 meters precision for raw signal of GPS. So 30 to 50 meters is not really usable for most applications requiring geolocation. Just to give you a sense of how LoRa architecture is built, so there are end devices spread in the environment, any small nodes or small device that communicate with gateways. Gateways are like antennas, also spread in the environment, on tower and things like that. And then those gateways communicate with with the Ethernet, and then there are, of course, servers processing the data at the end. So in our project, we want to improve the accuracy of those LoRa systems using machine learning. So just to give a bit of sense of how it works, there are mainly two different systems to do geolocation that are used: time of arrival, which is being used with GPS, and time difference of arrival. So time of arrival, we have as I said, used for GPS. We have an end device which has a precise synchronized clock. The timestamp on the end device needs to be precise, and the message is sent to all the gateways, and then the gateway also has this precise timestamp, and they can work with that. So this is GPS. But the advantage of LoRa is that this device here does not need at all to be precisely synchronized. It doesn't even need to have a clock. It just emits message, and the message are received by the gateway, and that's the gateway which have a precise clock which timestamps the message at 30 nanoseconds with a 13 nanoseconds precision. And this, when a message is received multiple times, so we have an ID of the message, so we know it has been received by multiple antennas. And with this TDOA, we can then put the location of the end node, or guess the location of the end node. Of course, in the context shown here, there is a direct line of sight, which is the ideal best case scenario, never true in reality, right? If we have a city, there will be buildings, something like that. And this is where our project works. In a non-line of sight scenario, when you have your end object maybe here, some signals may be blocked by buildings, so the gateway will not receive a signal. Some signals might bounce back against walls or buildings, and this might impair the precision of the location, because if the signal bounces here and goes to the gateway, then the gateway believes the device is much further than it actually is. So we have to find ways to cope with that problems. And this is the first problem or challenge. The second challenge is that real data is not yet available. There is no real data because the technology is quite new. They are currently deploying antennas in Switzerland and in other places. So there are no big data set of data having been collected with LoRa. I'll come back to that later because now we have some data. I'll come back at the end of the talk if I have some time. Now there is some data available and we have already collected a small data set to see what works. So knowing these two challenges, the idea of the project was to use fingerprinting techniques, I'll come back to that, and machine learning to improve the accuracy. And because we don't have any data, we need to build a simulator to generate some data to work with. The idea of fingerprinting is to go in a building or go outdoor with a device that has a GPS on it and a LoRa device. We move, we take a value, and then we move one meter, we take another value, and so on. And this gives us a map of errors of the LoRa protocol. So here, for example, here is an error of a LoRa protocol compared to GPS signal. So the GPS is seen as a ground truth, the true position. And then we can see, for example, that maybe here LoRa was not very precise, was not precise at all. There are small pockets here, maybe there was building around, so the signal was not good. And using this type of cartography, we can learn, the machine learning algorithm can learn from that, and it knows that if the signal received resembles this, maybe it should correct it, and this can improve the accuracy of the geolocation. Of course, this work is a work in progress because there's no real data, so we build a simulator to generate the data. And just for you to know, this is not a reference map of LoRa, this is just an illustration example, but basically we build the same map in our system. So of course this requires sending people outside and gathering data, which is not the most interesting job ever, but still has to be done. Always like that in machine learning, we need data. So the idea of the algorithm, as I previously briefly mentioned, is that we get input vector. It's a time difference of arrival at every gateway. We get all the gateway, we try to get the time difference of arrival value. We feed that to our model, whatever it is, algorithm, and then we get as output the corrected location. When it's learning, when we are training the algorithm, we actually have here the output of the algorithm and the GPS value, considered as ground truth, and we always correct the algorithm according to that until it's giving us the best results possible. A few words about the methodology. Now that has been used in this study. So as I said, no real data. So the first step was to try to build a simulator to generate some data. The idea or the goals behind these simulators are twofold. The first goal, of course, is to get data to be able to test algorithms before we actually have real data and start building them, testing them, and investigating the results. The second goal is to investigate if transfer learning would be possible. So the idea, instead of being forced to hire someone to go in all the cities of the world to do fingerprinting, we can simulate data using a map of the environment with heights and buildings and everything. And using this data, then we can transfer what has been learned. We can generate again simulation of the signal and transfer that to reality with only a small data set in reality. This is not part of this study, but this is for future work that could be done with such a simulator. Just a few words about how we did the generation of the data. The data was generated. So the first step was just to choose some random points in an area. So this is the ground truth. We know the exact latitude and longitude of the selected point. And because we wanted to mimic reality, we needed a GPS data set, right? GPS has also some noise, about 5 meters of error. So we built a GPS data set by just adding, we have a position in green, I guess. In green is the real position. In blue would be the position as measured by a GPS device. It's not the true one, right? We simulated that, we generated. So we added some errors, and this is for us our true data set, because in reality we won't have the exact measure, we always have the GPS value as a base measure. And then for the LoRa data set, it's a bit more complex, so we added 3 kinds of noise. The first noise is just a systematic error at the gateway, because the gateway, the signal is 30 nanoseconds, so there might be some errors, and this can introduce about 5 to 10 meters of error in the precision of the signal. So we introduced that as the first noise. The second noise is to kind of simulate bouncing of the signals depending on the location of the emitted signal. So we generated kind of some circular mask. These are circle, right? Just the thing that didn't do it correctly, but this is circles, and those circles also generate noise. So when you have a signal that is emitted from here, some noise is applied to it, depending on its position. If it's overlapping, then the two noise will be summed, right? So this kind of simulates the fact that a building might impair a signal and things like that, depending on the position of the end node. And then the last noise that was added is not a number of values. So this simulates that a signal was blocked by a building and was not received by a gateway, basically. So here on this figure, it's just a small example of visualization of a data set that we created. Of course, in reality, the area is much bigger and there are much more points, but if I put all the points here, you would just see nothing, right? Once we had data, the next step was doing some data processing, the first step of any machine learning application or work. The first proposing step was handling not a number, because most algorithms don't like to receive not a number as input. It's not really informative for them. So what we did was think about four impute approach, to replace those not a number value. The first idea was just, if a signal has a not a number value, we just discard it, which removes a lot of the signal from the data set. It's not ideal, but it's still a solution. The second solution, which does not make sense in this context, but is largely used in many machine learning applications, is just to, if we don't have value, we take the mean of all values of the vector. It's really a naive approach and doesn't make sense, but we wanted to test it. The third one is the same, it's input median. Median instead of the mean of the whole vector, we just take the median of all values. The last one is a bit more complex, it's impute KNN. When a value is missing, we're looking in all the previous training examples or input vectors that we have, and we're trying to find the closest one. The 5 closest one, which are resembling the most our actual vector, which don't have any not a number values, and then we're just replacing the values with the previous one. All those values are not ideal, but this is the first IDs that we had. Then we tested 3 algorithms, random forest, and then neural networks with wider or deeper architectures. We selected just 2 architectures to do some tests, and then long short-term memory algorithm that has been selected to. We already have a version of LSTM working, so we just wanted to apply it. It was quite fast for us. Thank you. So now let's get to the results and discussions. we did 3 tests. I just first start with just general information. N is the number of elements, is the size of the data set, the number of samples measurements. GW is the number of gateways that were generated. And then those are the input methods that we selected. And of course, the results are shown as error measure, root mean square error of the measurements outputted from our algorithm compared to the GPS signal. For random forest, we use grid search to find the best hyperparameters, and then we selected, according to our empirical test, the best values for neural network. I will not go through all these tables because it's not really interesting. I will always have a take-home message. So for this graph, we wanted to infer the number of gateway, and the best ideal number of gateway is 7 gateway to get an error below 50 meters. Sorry. And then as soon as we have, for example, 20 gateways, the error reduced dramatically because we have better precision, of course. We have more information as input. The second test was the loss function and the net number handling. We wanted to see the impact of the loss function chose to optimize the algorithm. The take-home message is that the mean square error seems better to work better with neural networks. Mean absolute error seems to work better for random forest. And the remove and KNN approach, as hypothesized, work better than the mean and median, which don't make much sense. There's a huge difference if you look between the mean and median and the 2 other ones. And what was curious, it also intrigued me when I read the article, is that LSTM, long short-term memory algorithm, works a lot better than the other ones. Just for reminder, LSTM is mostly used for sequential data, temporal sequential data. In this case, we don't have any sequential data. It's not just a single input vector, so we don't really know why this happens. And I discussed a bit with Francesco, and we are curious to investigate further why. The third test was to investigate the impact of the dataset size. Of course, we probably all know that the bigger the dataset, the better. This is still the case in this study. When we start with a really small dataset of 2,000 samples, the results are not that good. And then when we go on with much more values, we get to a value below 9 meters with a long short-term memory and KNN impute methods. Something also interesting here is that for the random forest algorithm, when we go to a huge data set, then the performance of random forest gets really good. So of course, because random forest is good for generalization, right? Right. A few words about the conclusion perspective. So the regression, our approach based on regression doesn't need to know the coordinates of the gateway. This is some advantage. We have the gateways, we have our settings, we train the algorithm, and then it works. We don't have to feed it any information. The main drawback of our approach is that if someone builds a new building in the city, then the fingerprinting approach is not, they are introducing new error, and we should, again, rebuild the model. If a gateway goes down, again, the model is not really valid. But this is a common problem for any fingerprinting technique used. Also, open question, the validation of the simulator. We still have to validate that the results obtained with the simulator, with generated data, will do the same for real data. This is something that we don't know at all. And then the next question is why, as I mentioned before, I'm really curious about that, and I mentioned to my colleague that I wanted to see again the code, or I did it to understand why does LSTM perform better. It's really counterintuitive. We don't have any answer yet. And the third question is transfer learning. As soon as we have more real data, we can try to investigate a bit the feasibility of transfer learning. A bit of spoiler alert, so we have new data. After the article was written, we got some new data from the city of Yverdon-les-Bains in Switzerland. And what we've noticed is there's a lot of not a number. We assumed there would be maybe one not a number, a gateway would not receive a signal from time to time, but actually it happens a lot. And this is a problem, and the two approach here, impute approach, that were used in this study cannot be applied real data because of that. So we have to find another approach like a field. Just a few words. This is a view of the real data that has been acquired in Yverdon-les-Bains. And you can see this is the end node, right? And as soon as there is a circle around the gateway, it means that the signal was received. And even when a node moves maybe from 1 meter, really different patterns of gateway receive the signal. So when you move really a smart side position, the pattern can change a lot. And this is really not good for machine learning because it means too much variability, it's not good. And so probably all of the studies that have been performed here have to be adapted or to adapt to these problems. And I guess this is quite interesting for to know that information for people. And that's it. Thank you for your attention. And as I said, I will try to do my best to answer your questions. If you have really precise questions, you can ask my colleague or read the article, which is quite understandable.